recorded.
Got it.
Please close your video. Oh, let me charge it.
Do you know how I can get rid of this little bar at the top?
Have no idea how to do that. Hi, Katie.
Hello.
Hello.
Yeah, maybe we can start. Like, Jehan, please record the talk right now. Maybe I think I will. Is the slides reading right now? James, are you ready to present? Okay.
Yeah, well, no, because can you see this little thing that shows like the mute button and the stop video and so on?
No, I didn't see it.
Oh, you can't see it? If the slides look good to you, I'm ready to go.
Yeah, the slides look good to me, yeah.
Okay, great. I can't see if anyone raises their hand, by the way, so just call out. Yeah.
Okay. Yeah, if you have any questions, just feel free to unmute yourself. Yeah. Okay, so it's my great pleasure to introduce today's speaker, James Murphy. And James actually worked in mathematical data science, and his research interests include the applied harmonic analysis. And he has done a lot of interesting work in clustering and more recently in the optimal transport, like the interplay between optimal transport with data science. And today, actually, he will actually talk two different works in these two different directions. So welcome, James.
Hi, everyone. Thanks, Sway, for the invitation. Yeah, really glad to try out some new material. So yeah, as Sway said, my name is James Murphy. I'm in the math department at Tufts. So the title of this talk is Geometry and Data Science, Graphs, Manifolds, Barycenters, kind of vague. I guess the overarching philosophy here is that both of the things I want to talk about are related to, how to do learning in high dimensions, right? So it's, I think, almost like a matter of religious, article of religious faith that high dimensional learning problems are hard. I think that there's many different ways to kind of articulate this curse of dimensionality. The one I'm going to return to is that distances in truly high dimensional spaces aren't very meaningful because things tend to be very far from their nearest neighbors. So the approach that the two approaches I want to think about are ways of essentially changing the metric for high dimensional data that can pick up on different latent structures in the data. And the two approaches will kind of be linked in the sense that they're both in a sense geometric. One is maybe a little bit more, I would say, classical in the sense as essentially using manifold structures in data to do a kind of unsupervised learning. And the second part is going to be a little bit more recent stuff that's kind of a topic a little bit more new to me. So I actually would enjoy getting feedback from people who know a lot about this stuff and thinking about getting some traction by essentially parameterizing high dimensional data through Wasserstein Barycenters. So the idea in that case will not be to exploit manifold structures as sort of a way to break the curse of dimensionality, but to think about essentially something like a subspace parameterization of your data, but not in Euclidean space, but in this sort of infinite dimensional Wasserstein space. So I'll try to make that idea come through a little bit. So the first part of the talk is on sort of essentially clustering with a particular type of data-driven metric that's going to allow us to beat the curse of dimensionality. So the problem for this first part that we want to focus on is clustering. So this is essentially machine learning with no labels, right? So one way to phrase this is that my observables are a sample from some probability measure. In this case, we're going to assume it's an IID sample, albeit that's not really the point of this talk. The point is this measure has structure though, right? So I'm going to imagine that mu is not arbitrary, but it's some kind of mixture model. And the mixture atoms here, or sort of latent components, are really the structure I'm trying to infer. So I'll parameterize this as saying, this measure mu is sum from k equals 1 to capital K of WK times mu K, so plus a noise measure mu tilde. So I'm thinking each mu K is like somehow a simple measure, like supported on some kind of structured set. And the mu Ks, so the WKs are just the weights by which I sample from them. So on the right, I'm just showing you an instance of a sample from one of these measures. So here we're imagining that like capital K is 4, because there are these 4 latent clusters, and the mu Ks are sitting on these like one-dimensional or approximately one-dimensional subspaces. So the question that we're interested in essentially here is, if I tell you the model specifications here, right? If I tell you, for example, what capital K is, can you tell me, which xj's were generated from which mu k's? So essentially to do it like a labeling problem, assign each point to which measure generated it, but without any training data. So the content of this part of the talk will also get into maybe issues of model selection, right? How can I identify the correct choice of capital K? And are there ways to maybe parameterize possible choices for the numbers of clusters, depending on kind of how you squint at the data? And we're going to do this by developing a family of metrics that captures some of this latent structure. So just a quick overview, what do people do for this? It's a very well-studied problem, unsupervised clustering. Maybe the most standard one is going to be what's called k-means clustering. Essentially, this partitions your data and assigns labels by solving an optimization problem. So I essentially compute a certain number of partition elements, right? These are the CKs. I compute the centroids of each of those, and then I make assignments of each point to the nearest centroid. I can write that as this optimization problem over the space of centroids. Okay, it's a thing you can do. It has combinatorial challenges. It's an NP-hard problem, but we're not going to focus on optimization so much. We really want to just think about what kinds of things does this work well for. It works well essentially for well-separated spherical-ish data sets. So essentially, I want to be able to draw balls around each of the clusters and not have those balls intersect too much. So I just ran k-means in like MATLAB on the right and showing you the red dots are these centroids, and the labels are shown with the colors. It's really easy to come up with stuff where this doesn't work, right? And the reason is we're sort of bringing in like a prior expectation to what kinds of data this can handle. So non-spherical things are not going to work so well for this, even though they're in some sense can be very simple, right? So this data set consists of like these 2 kind of blobs, and then this essentially one-dimensional manifold corresponding to the smile. K-means just isn't adapted for that. So what can you do? I'm going to talk a little bit about a very kind of classical approach to this called spectral clustering that has several really interesting interpretations. The one I'm going to focus on, the interpretation is going to be that this induces like a new metric on the space of data points. And that metric is more revealing than the Euclidean metric, albeit this also has interpretations in terms of things like relaxing combinatorial graph cut problems. So the idea of spectral clustering, which goes back to several different authors, Shi, Ng, Michael Jordan, so on, is to take these observations and essentially build a graph on top of them and look at the spectrum of that graph. And that's going to give me a ton of information about the latent positions of the points and really who's close to who. So algorithmically, we observe our data x1 through xn. We build this graph wij, which is going to be the kind of connectivity between the ith and the jth points. And the first kind of design point is I need to pick a way of comparing the observations. So I'm going to pick a metric d and essentially kernelize that metric when I build this weight matrix. So you can think an important question here is how do I pick D and how do I pick the scaling parameter sigma so that things that are supposed to look close together are appearing close together and things that look far apart are far apart. So I'm showing you on the right bottom this matrix, which is this weight matrix corresponding to the SMILE data in the case where your metric is Euclidean and I pick a particular choice of sigma. So what information can you glean just from looking at this? Well, okay, I have ones on the diagonal the way I've defined this. Everything is distance 0 from itself with the metric. So when I hit that with the heat kernel, it goes to 1. And then I see, okay, this first block is like the SMILE. I get sort of decay off of it because things on opposite ends of the SMILE are pretty far. And then I have these little blocks on the second and third. sort of block regions that are more homogeneous, right? And that's because these eyes in the clustering are pretty close together. So the standard algorithm would be to build a graph Laplacian out of this. There's many ways to do this. Throughout this part of the talk, we're going to be thinking about the symmetric normalized Laplacian, albeit you could do the random walk Laplacian, for example. So I build the graph Laplacian. This is positive semi-definite, has basis and orthonormal basis of eigenvectors with associated non-negative eigenvalues. And we're going to, in this interpretation, rewrite our data points according to their embedding in the coordinate space of the lowest frequency eigenfunctions. So I can think phi1 here is essentially constant. It is constant. Phi2 is sort of the next lowest frequency eigenfunction. There's a whole analogy with Fourier series here, thinking of Fourier modes as the eigenfunctions of the partial differential operator, the Laplacian, and that metaphor carries through here. So we're essentially representing the data points in terms of these Fourier modes, and that turns out, for all sorts of good reasons, or some folklore reasons, to be good embedding for the data if you want to cluster. So what I'm showing you on the right now is if I take those SMILE data points and represent them in the phi1, phi2 latent space, and the point here is that SMILE has contracted a lot. So now it's a little bit easier for something like k-means, which again is looking for clusters that are essentially can be fit inside non-intersecting circles. It's going to be easier for that algorithm to correctly identify the latent labels. And in fact, yeah, it works well. I mean, this SMILE data set was kind of like a nice toy example in an old paper by Andrew Angier, Weiss, and Michael Jordan for why this kind of spectral approach works. Okay, so what I'm interested in for this is trying to understand good metrics to use for spectral clustering. That is, when I'm building this underlying graph, I have to make a design choice in terms of which metric to use. Obviously, it's quite natural to use something like a Euclidean norm between two objects, where I take norm of x minus y, and that should be like my latent metric here. But what we saw is that you can get, in some cases, much stronger theoretical guarantees and better performances by using metrics that are just a little bit more data adaptive. And so the kind of theoretical target we were interested in was one in which we could do model selection by basically using the metric. So we wanted to find a regime in which this kind of heuristic that's quite common in the literature for how to detect the number of clusters, which is to say, look at the gap between the largest gap between consecutive eigenvalues. We wanted to understand, when is that actually going to work, right? And what we saw is that by designing the metric in a particular way, we can make that happen. And so the metric we started with for this, line of inquiry was, again, like I said, a data-dependent one, and it's essentially like a kind of L-infinity geodesic on the graph. So what we do is we say I have my set of observations, and I'm going to put some Euclidean edges between these things, right? So this definition is going to be, we're going to imagine a complete graph with these xi's as the nodes, and between every pair of xi's, there's an edge whose weight is the Euclidean distance. And we're going to do essentially a shortest path problem in that graph, but we're not going to give the penalty or the value to a path in that graph equal to the L1 norm of the edge steps, or that is to say, we're not going to define the cost of a path to be the sum of all the edges in it. We're going to define the cost of a path to be the maximum edge in that path. So we define the longest like path distance between xi and xs to be the minimum over the space over all possible paths of the maximum step size in the path. So one way to think of this is like it's like an L1 geodesic problem on the graph, except I'm replacing L1 with L infinity. So I'll just say a little bit about computation here, albeit it's not the most important part of this. This is not actually so hard to compute. And one way to convince yourself of that is essentially a shortest path problem with a weird metric, with L infinity metric. So a version of like a Dijkstra type algorithm works just fine here. And in fact, we'll see in the sort of second part of this first part that of all the geodesic type distances on the graph that have this kind of structure, this is in some sense the easiest one to compute. So it's really not trouble at all. why do we like it for this unsupervised learning problems? Essentially, it gives you a nice model class of data for which the following claim is true. Things in the same cluster are close together, things in different clusters are far apart. And just as a little illustration, what I'm showing you in both of these images is a sort of canonical clustering data set, the 2 moons data set. And I'm highlighting a point circled and showing you on the left all the Euclidean distances from that circled point, and on the right all the longest light path distances from that point. And what you're seeing essentially is all the points in the same moon as the circle point look really close in this longest light path distance, and all the points in the other moon are very far in longest light path distance. And that's just not really the case for the Euclidean distance. I mean, essentially, Euclidean distance is constant on L2 balls, so you wouldn't expect that for these kinds of non-convex sets. Right, so what we did do is we wanted a sort of large model class for which we could say, if we do spectral clustering with this longest light path distance, then we're going to be able to, first, the kind of lower hanging fruit would be, can we prove that if I run spectral clustering, right? That is to say, if I run k-means on the eigenvectors of a graph Laplacian coming out of using this metric, will I label everything correctly? The harder question is, can I make this eigengap heuristic work, right? Can I guarantee that I am going to detect the number of clusters correctly? And so the motivation is basically, what this longest light path distance does is that it makes decisions kind of based on where density gradients are large. So what I'm showing you on the left is the weight matrix for this data set here in Euclidean distance versus this longest light path distance. And what you're seeing on the right is these sort of not quite, rank 1 blocks, but like approximately rank 1. And so what that's saying is that all within a cluster, all the distances are pretty close together. And then everything is far from everything else, right? Because all the off diagonal entries are very close to 0. So this is on the right, you're seeing something approaching like the ideal structure for spectral clustering. So the theoretical model we consider here is, ultimately we want a finite sample bound. We want to say, if I sample from my probability measure mu, and I take at least this many things, then with high probability, all my dreams come true. So the way we were able to get sort of good bounds here was to consider that the clusters needed to localize on low dimensional sets, right? And what we decided to go for was to parameterize low dimensionality in terms of manifolds, right? So you can think of this definition that I'm writing here as essentially saying each of these support sets for these measures that make up the measure I'm sampling from, this mixture model, that they all need to look, when I zoom in close enough, like a little d-dimensional set, right? So this is essentially like a very kind of weak notion of manifold, right? There's no differential structure here. It just needs to be the case that when I zoom in far enough, it looks locally d-dimensional. And these kappa constants here is basically kind of capturing like the warpage of that, or like, if you like in manifold language, like a curvature. So we're going to assume that our sets are all sort of intrinsically low dimensional. Just for ease of exposition in what follows, I'm going to assume it's the same dimension for all of them, but doesn't need to be. So what we have are these support sets. These are like these script x1 through xk, and they're all living in some ambient space script x. And I assume each of like the constituent pieces is low dimensional in this sense. Now, the biggest restriction I have to make here from a model standpoint is that I can't allow these sets to intersect. I do not believe that this is ultimately like a fundamental thing, but for the theorem I'm about to discuss, it is necessary. So we have to have these non-intersecting support sets that I'm thinking of as like nice manifolds. And what I'm going to do is sample from them at rate n1 through nk. And I'm going to allow background noise, right? And the point is I'm going to be able to tolerate quite a lot of it with this metric. So I'm going to sample n tilde points from everything essentially in my domain that's not a cluster set. And what I'm showing you on the right is just like a simple instance of this. So here I would be in capital D equals 3 dimensions. I'm in unit cube in R3. And my cluster sets are sitting on these different edges. And then in between them, I'm sampling noise points from the sort of ambient background. So the key parameters here are going to be the minimum number of points I sample from any of the clusters, that's n min. And then ultimately, we're going to have something like a signal to noise ratio where n tilde needs to be not too big relative to n min. Just to make the algorithm work a little bit better, we incorporate a denoising step where I look at the distance to your K noise nearest neighbor in this LLP distance. And if that distance to that nearest neighbor is too large, I'm going to guess that you're a noise point, and I'm going to remove it from the data set. So there's sort of like this pre-computation step where we try to remove a little bit of noise, which we think is structure revealing, and then we run spectral clustering. So what can we say? We can say that as long as my number of noise points and tilde is not too big, okay, that's the sort of main condition here. Then if I run spectral clustering with the Gaussian kernel, essentially I can pick my parameters theta, which is the denoising parameter, and the scaling parameter sigma in the ranges specified by 1 and 2, so that I get what I want, right? Claim 1, the largest eigengap is between the kth and k plus first eigenvalue. So meaning that if I use the eigengap heuristic to estimate the number of clusters, I'm correct there. And then if I run spectral clustering on those k eigenvectors, I'm going to get perfect accuracy in terms of labeling. So there's lots of implicit constants here that depend on like the curvature of the manifolds and so on. I just want to say a little bit about the signal to noise ratio in equations 1 and 2. So the signal to noise ratio is going to be generous, right? It's going to allow me to tolerate a lot of noise when capital D divided by d little d plus 1 is large, right? And that's exactly when you're in a high dimensional space, but your intrinsic structure is low dimensional. So when that ratio, when there's sort of a big gap there, I do well. Equations 1 and 2, I'm thinking those are going to be good for me when the range is wide, right? So when there's a lot of choices of theta and a lot of choices of sigma. And it's the same story. When little d is very small compared to big D, range 1 is big. Similarly with range 2 in terms of the separation needs to be large relative to this denoising parameter theta. So in particular, I mentioned that we can't handle overlapping clusters. If delta is equal to 0, there's no choice of sigma that works here. So unfortunately, that is a constraint for this approach. I just want to give a little bit of insight into like why we, does this work well in practice? Like, does this theorem actually hold up? And the answer is, yeah, sometimes. So when we look at this coil data set, we took 16 of the image classes from there. So each of these clusters, if you like, is a very high dimensional object, right? It's an image in, I believe they're 32 by 32 pixels. And what I'm doing to generate a cluster is I'm taking like a base image, like a fixed rubber ducky, and then I'm rotating a camera around it. So in that sense, there's this notion that, oh, okay, yes, these are high dimensional observations, but each cluster is kind of like a low dimensional manifold that's basically parameterized by this rotation. So that story isn't quite true, right? That ultimately, even for that kind of simple image class, it's, maybe one doesn't want to use a Euclidean metric for these kinds of things. More on that in the second part of the talk. But this data set was sort of simple enough that even though it was images, if you constructed your graph with Euclidean distances and used this longest like path distance, you get very good accuracy for clustering. But more interestingly, you see a very large and persistent gap between the 16th and 17th eigenvalues. And what I mean by persistent is I can choose a lot of different sigma values for my Laplacian and see, oh, okay, there's a big gap between eigenvalues 16 and 17. So I'm going to estimate those, 16 clusters that way. So we thought this was kind of like a nice validating example for our approach. So I want to maybe try to convince you that this longest like path distance is really just one representative, kind of an extremal representative of like a larger family of path metrics. So I think the most classical one would be what you would see in like an undergraduate algorithms class, where what you're going to do is take your graph, define the distance between two nodes on that graph to be the minimum over all paths of the sum of the edges on that path, the so-called L1 geodesic or L1 shortest path problem. What we just looked at is sort of like an L infinity version of that, where I just take the maximum edge step. But we can interpolate between these things. And we do this with what's called the several different names in the literature. The one that we're sort of currently using is the Fermat distance, or the P Fermat distance. And essentially this is like the cost for a path in this metric is going to be the LP norm of the edges in the path. So longest like path distance is like taking P to infinity. And in fact, you get the convergence works out, generically speaking. P equals 1 is like your classical shortest path. So what we noticed and like about this is essentially P equals 1 if you want to think in terms of like, imagine sampling from a manifold. This is basically interpolating or trying to estimate like the geodesic on the manifold. So in that sense, it's very geometrically driven, right? It really cares about the structure of the support set of the manifold on which you're supported. P equals, or P going towards infinity, really cares mostly about density and then sort of where there are gaps in the density in the data. And then between that, there's some kind of interpolation between geometry and density. So just as like kind of an illustrative example that I think, I don't know, puts like a finger on the fact that unsupervised clustering is a little bit ambiguous. We have this just like little toy data set that I'm showing you on the bottom of this figure. It's essentially, it's a dumbbell, right? So it's a kind of classic example of like a manifold learning data set where you would say, well, if I do, graph Laplacians and look at the second eigenvector, I'm going to cut at the dumbbell middle, where I'm going to split these sort of two large balls into, down the middle. But what we added is a density gradient to each of the bells, right? So there's, essentially the density is not constant on the support set here. It dips as you go across these balls. So what we're seeing is that, okay, there's sort of several reasonable partitions here. The purely geometric one would be, say, cut down the middle. One that's based on like a density gradient would say, actually, we don't care about this sort of dumbbell region, this middle part. It's constant density there. There's no density gradient. The density gradient's in the middle of the bells at the end. So I should cut there. And then, maybe you want to combine both, right? Maybe you want to say, well, depending how I squinted this, both are reasonable. And what we like about these Fermat distances is that they essentially capture this spectrum of possible interpretations. So what I'm showing you is I'm taking this same data set and computing the spectral graph embedding that I get from building the graph Laplacian with these Fermat distances. And I'm showing you the embedded representation using the second and third eigenvectors of the Laplacian. So one way to think about this is, okay, looking at P equals 1.2, if I were to threshold phi2, but this is like the classic spectral clustering approach, take phi2 and cut it off at 0, or maybe if you're a little bit fancy, you would cut it off somewhere else. There's no way to really cut along the phi2 axis so that I develop a partition which cares about density, right? The density is really orthogonal to phi2 here, right? I mean, I can cut along phi3 and somehow pick up density regions, or density separated regions, but when I pick P equals 1.2, the latent structure is really all about geometry. Now, if I go to being P much larger, you see I've actually made a very strong separation along these density gradients. So all the decisions there are based on density. So I'm thinking P equals 5 is kind of like a surrogate for P equals infinity. It's actually a very fast convergence of these Fermat metrics to the longest light path metric as P gets bigger. So P equals 5 is pretty darn close to the longest light path metric. The interesting case is P equals 2, because then now imagine you're thresholding along the phi2 axis. If I threshold at 0, yeah, okay, I'm going to get the same geometric partition as I would in the P equals 1.2 case. But now there's separation, but across the density regions also. If I threshold it like phi equals 0.2, or phi equals like negative 0.25, then I'm going to be able to cut off these density separated regions. So P equals 2 really has like aspects of both geometry and density sitting in it. And I think that's pretty interesting. So one point I want to make is that computing these things is, one can of course use like a Dijkstra type algorithm, which would say essentially, you give me the graph, I'm going to tell you how to take this combinatorial optimization, which is to say optimize over all possible paths. A priori, that's NP hard. It's a lot of paths to check. Dijkstra's algorithm lets you do that fast, right? In a manner that sort of scales well with the number of edges rather than exponentially with it. But from our perspective, we're really thinking about like data is coming in, right? And I don't have a graph to start with. So I'd like to build a graph which will allow me to compute these Fermat distances easily. And the construction that we were interested in is we'd like to do this fast, right? We'd like to have a lot of data come in and be able to quickly compare two different points. So our hope is that we can actually do these Fermat distances, not on a complete graph, right? Which as soon as I'm talking about a complete graph here, my computational complexity is at least n squared, right? I have to write down all the edges between endpoints, n squared. I'm not going to be able to run that for a big problem. So I'd actually like to be able to do the Fermat distances on a nearest neighbor graph, Euclidean nearest neighbor graph. And of course, this is something you can do, but the question is it, what am I missing, right? Am I going to be losing a lot of information when I do the nearest neighbors graph rather than complete graph? And the answer is, it depends on P. It's kind of interesting. When P is very, very large, no, you can actually do this on like a number of nearest neighbors that's very, very small. When P goes towards 1, you can't do this, right? So if you want to get the kind of true geodesic distance on the complete graph, you're out of luck when P is 1. But for P greater than 1, you can do this with the nearest neighbors graph. And so the theorem we have is basically that, as long as my measure is supported on like a nice manifold and the density is like bounded away from 0 and away from infinity, then as long as I take K, essentially scaling logarithmically in the number of samples, running the Fermat distances on that K nearest neighbors graph is the same as running it on the complete graph. The interesting point is these constants, right? Because these constants depend exponentially in the intrinsic dimension. Note that 4 over 4 to the 1 minus 1 over P minus 1 converges as P goes to infinity to, I think, like, something not too crazy. The challenge is as P goes towards 1, you get blow up here. So this bound is very, very poor as P goes towards 1, but it's quite good as P goes to infinity, albeit you still end up with like a small constant to the power of D. So basically you can run this stuff on large data sets just by doing nearest neighbors graphs. And then of course you need to be able to compute a Euclidean nearest neighbors graph fast. That's an incredibly well-studied problem that I won't get into. And the thing I'll sort of end with here is I think this problem is almost like more well formulated in the continuum setting rather than the discrete one, meaning that all the constructions I've discussed so far have said, take samples from this manifold, build paths using that. But like I'm sampling from a manifold, right? So I have some measure on this manifold, right? So in particular, let's assume I have like a probability density on the manifold. Why not just like talk about the paths with respect to that density somehow? And where instead of doing like L2 distances between points somehow and weighting them in a particular way, I use the Riemannian structure to sort of think about how much paths are going to cost. So we can define like a kind of continuum limit analog of this Fermat distance that is basically saying, okay, basically do like a geodesic on the manifold, right? So it looks exactly like what you'd have for the L2 geodesic, the kind of standard one, but now I'm going to weight by the density. Right. So when P is large, this script LP is going to really penalize going through low density regions, right? Because I'm doing 1 over my density times, the normal Riemannian tensor. So this sort of is the correct limit definition. You get sort of convergence in all the right ways. But now we can start talking about essentially operators on this manifold using this metric, right? Using the metric that comes out of equation 1. And the way we can sort of make this work pretty easily is by noting that our metric LP is essentially equivalent to rescaling the Euclidean distance to care a lot about the density, right? So we kind of think of this as like a local equivalence result on the continuum formulation of the Fermat distance with a rescaled version of the Euclidean distance where the rescaling is done by density. So it's a little bit, it's technical. Essentially, it's saying, well, I need to have my points be close in the geodesic distance on the manifold, but once I'm close enough, the Fermat distance and the rescaled Euclidean distance are pretty close. And this gives us a way to understand what these if I were to build something like a Laplace Beltrami operator with a Fermat distance, what can I say about the spectrum of that, right? And that I think would really complete this picture of thinking of these Fermat distances as kind of interpolating between density-driven and geometric structures on the data. So that's ongoing. Okay, so I would like to change gears, and for the next, I guess, like 20 minutes or so, talk about some very recent work that we've been doing that takes kind of a different approach to addressing this cursive dimensionality problem. So to connect it to what I just did, right? I mean, ultimately the Fermat distances try to, account for global patterns in the data by using these types of paths, right? And this is the idea behind a lot of manifold learning. This is the idea behind diffusion maps, the idea behind Laplacian eigenmaps, isomaps, all those things, is that I can make kind of global inferences by taking like local Euclidean calculations and somehow stitching them all together. Right, so this sort of this maxim of like think locally, fit globally. It's I think there's actually a paper with that name, but that it might not work, right? I mean, even the local Euclidean constructions may be the wrong thing to do, right? And in that case, like the whole manifold approach doesn't make a lot of sense. And so this is just a very kind of cheap toy example, but I'm just imagining a data set that consists of like black and white images, and the images are like all black. Except there's one white pixel in each of them, right? And I want to be able to, like, let's say, do clustering on the space of images. And you might say, okay, well, if I learned anything from the first part of the talk, it's that like, if I do these local graph constructions, I can deal with the fact that these are high dimensional objects, that they're, number of pixels images. Okay, I'm just going to do local Euclidean distances and stitch them all together. But the local Euclidean distances don't mean anything here, right? Everything is sort of equally far if I do, L2 norms between these images, like after vectorizing them, right? They all differ in the same two places. So in some sense, the metric is equally going to give the same penalty to any pair of images that aren't the same. So can't use it really if I want to make any kind of discriminating decision. What I really need is a metric that will, be able to capture this idea that two images here should be similar if the locations of these pixels are themselves similar, right? They should be able to capture the support of these images and the distance between that. And that is something that Wasserstein distances do. So, very, very well studied topic. I am going to make some kind of like simplifying assumptions here. So we're always going to be assuming that our measures that we talk about here have densities with respect to the Lebesgue measure. And so in some cases, like if you're familiar with this literature, a lot of the complexities of, Monge versus, Kantorovich problems kind of simplify a little bit. So we're just going to define the Wasserstein metric between two absolutely continuous measures, mu and v, to be the minimizer over all push forwards, t, which send mu to nu. And so we minimize essentially the distance between the map's evaluation of x and the base point, right? So essentially looking at all of the possible maps that carry mu to nu, and we want to do this in a way so that stuff is moved as little as possible in an L2 sense, right? So this is just below, just a technical definition of this push forward. I just want to give a picture that I stole from Matt Thorpe's notes on this. And this is just this idea of the push forward, right? I need to look at maps that carry one measure to another. And so I'm going to take that set of maps and find the one that does it in the most efficient possible way to talk about this W2 metric. For our purposes, it is important to do W2 because we're going to take advantage of some special structures of that space. But this problem could be defined for other, Wasserstein metrics. I could do a different power than 2 in the exponent inside the integral, but we really need that in our case. So the insight, or I guess the sort of ideas that we're interested in here are thinking about like what's the right way to combine things in Wasserstein space. We were motivated by thinking about like, manifolds are in some sense generalizations of subspaces, right? I mean, a subspace gives you a low dimensional structure, but also it's a way of combining things, right? It's sort of all the different ways you can take, basis elements, let's say, if it's a genuine subspace, and add them together, right, linearly. And then the manifold just gives you like a way of kind of stitching a bunch of subspaces together in a consistent way. So what's the way to combine things in Wasserstein space? Well, one can add things together, but this winds up giving some kind of strange objects, right? If I just take a straight up mixture model, and I'll show a picture in the next slide of why that's maybe not so good. So the one way to think about this is to think about the idea of averaging in a variational sense, right? So I can define the average for just like a bunch of numbers to be the number which minimizes the average square distance between my observations, right? So I can, of course, it's a theorem, I guess you could say, that solution is what you get by adding everything up and dividing by the number of observations. But I can also just purely define the average variationally. And that's the notion of Wasserstein Barycenters, is to define the correct way of combining a group of measures with weights given by something, some lambda in the simplex, to be the measure which minimizes the weighted sum of Wasserstein distances between nu and the mu i's. So the construction is I take a set of coordinates, lambda 1, which is just a vector in Rp. So I'm imagining I have p different measures I'm trying to combine. And these lambdas are just the weights that I'm going to use to combine them together. And I solve this variational problem, the minimum over all absolutely continuous measures of essentially the weighted distances between nu and my observations mu I. So not clear at all that this makes any sense. In our context where we have absolute continuity and so on, this is well defined and unique. And I want to argue that this is the kind of correct way to average in the space of measures. And I think just, there's sort of many justifications for this. One I think is sort of geometrically satisfying, given this example I started with, is imagine I have just like a bunch of Gaussians, right? So that's these 4 little images on the top, and I want to combine them. I mean, I could certainly do this without Wasserstein things, right? I can just define the combination of these measures to be the mixture model associated to them, which would just say, okay, I'm going to define a new measure that says sample from one of my constituent measures, with a particular probability, right? So you can think I have in this case like a 4-sided die. I roll it, I pick which measure I'm going to sample from, and then I sample from it. That doesn't preserve a whole lot of structure, right? So what I'm showing on the bottom left is the Euclidean mixture you get from combining the top measures. And you can see it doesn't look like a whole lot. But if I do this Wasserstein Barycenter, it does preserve some structure, right? So these are all Gaussians, sort of theorem that the Wasserstein Barycenter will itself be Gaussian. But that's, more is true than that. And I'll leave it at that for today, that the Barycenter, it does preserve some kind of intrinsic geometric structure of these measures in a lot of cases. So how do you do it, right? So I want to pose this problem of I give you the mu i's and I give you the weights, these lambda i's. So I'm giving you a collection of p measures and a sort of weight vector, lambda, and I want you to give me the Barycenter, right? So I mean, there's many parts to this problem. Does it exist, right? Does it, have any sort of nice mathematical properties? Can you give me statistical procedures for estimating it? If I just give you access to, say, observations from UI, can you give me a computer algorithm that does this quickly? And the answer is yes to all of them. Okay, so this is pretty well studied mathematically, statistically. The sort of rates of estimation are well known. There's sort of several ways that are quite good for computing this thing, given observations, depending on if you care about randomness and so on. So I just want to show on the right here, I'm calling this the synthesis problem, just to get some some of the language of harmonic analysis in here, which is how we were thinking about this. The synthesis problem says, you give me the reference measures, the 3, the 8, and the 9 that are at the vertices of this triangle. And then I give you the relative weights to combine things, right? And then tell me the new measure. So this is on the inside of this triangle. These are all the different ways of combining the 3, the 8, and the 9. using weighting coordinates that are multiples of 1/3. So if I look at the 3 and the 2 that are nearby it, this mostly puts the energy at 3, but it gives you 1/3 of your energy from 8 and 1/3 of your energy from 9, respectively. So the synthesis problem says, give me the 3, the 8, and the 9, and lambda, and then you need to compute the interior of this triangle. So the approach we were interested in is thinking about all the different kinds of measures you can get as barycenters of a fixed set of base measures, right? So we're going to call this the barycenter coding model. And so this, to define one of these guys, you need to give me a set of reference measures. And then I'm going to define Bary of that set of measures as all the things I can generate from those base measures. So essentially, it's this idea that I'm going to identify an element of Bary of mu I with its coordinate representation. So you can kind of think of this as like the span of these measures, but where I'm not doing like linear combinations, but instead interpolating in Wasserstein space. So the question we're interested in is sort of the dual problem to the synthesis problem. So synthesis says you give me the measures and the coefficients and tell me how to construct the thing. Here I'm saying you give me the sort of one measure and the references, and I want to learn the coefficients, right? So I want to minimize over the coefficients associated to all the things in a particular set of barycenters that's generated from a fixed set of known measures. And I have my observation mu I. So this is like mu 0. So this is like decomposing mu 0 with respect to the reference measures here. So if I go back to this picture of the images, the problem now is 3, 8, and 9 on the vertices are known to me. And then I show you one of the interior images, and I want you to tell me the mixing weights. Okay, so it's like the inverse problem, going from observations back to coefficients. And this is less well studied. There are some computational methods from Pire and Katuri. We're going to propose one that we believe is quite general and enjoys some statistical guarantees. And I'll just note that one way to think of this is, this is potentially a well-defined problem, even for measures that are not actually in the barycentric span, right? Albeit if it is in the barycentric span, then this minimization problem will have a solution at 0. Okay. So the observation we have is that this problem can be solved in terms of a particular kind of quadratic program. So suppose I have measures mu1 through mu p, which are my reference measures, and then u0 is my observation. I want to check, for example, if mu0 is in the barycentric span of these reference measures. So is there some choice of coefficient which will yield for me that mu0 is the barycenter of mu1 through mu p with respect to these weights? So we can solve this by looking and asking if this quadratic program lambda transpose a lambda has a solution being equal to 0. And the key point is that this quadratic program is small, right? It is p by p, okay, where p is the number of reference measures rather than the intrinsic dimensionality. And the coefficients, the aij's, are defined in terms of the optimal transport maps between mu0 and mu I. So in this sense, one might be concerned you have to compute the optimal transport maps between all of the different measures, but you only need to compute it between the observation mu0 and the reference measures. So the way I think of this is that, okay, Ti of x is the W2 optimal transport map between mu0 and mu I. And so when I subtract the identity, I'm basically looking at the displacement of a vector when I transport from mu0 to mu I. So I'm taking inner products of these displacement maps and then averaging them. So essentially, the terms of this integral can be thought of as like average angles between displacement of these maps. So the main idea is basically to try to use calculus, right? Like you'd like to understand when the minimizers, basically when solutions of the gradient of this variance functional, which is the thing we're trying to minimize in the barycenter computation, when setting that equal to 0 works, right? When can I use sort of first order optimality conditions? And the observation is that this can work under some mild assumptions on the measures. So I can use calculus, great. And then to observe that actually the gradient of this variance functional is exactly this quadratic form, right? So 2 parts, right? Doing a computation to show what the gradient of this quadratic form is in terms of these transport maps, and then to show that first order optimality conditions is sufficient in this case. So, okay, so we can establish inclusion in this barycentric set. But now what I want to do is say, okay, suppose I give you observations instead of access to the measures. Because this theorem is maybe a little, this is it's an idealized theorem, right? It assumes that I can compute these transport maps. It assumes I can integrate with respect to mu naught. What if I just get samples from the measures instead of the measures themselves? Well, I would like to still be able to do something. So I just want to, have one slide to introduce this idea of entropic regularization and optimal transport. So now we're thinking entirely in terms of discrete problems. So what is the discrete analog to the optimal transport problem? So I didn't talk about the Kantorovich formulation, but instead of thinking about maps between probability measures, I can think about couplings between them. And there's a whole sort of amazing mathematical history between why you want to, how this came up, 150 years after the original problem was posed. We can talk about this afterwards if you're into like that kind of philosophy of science and so on, history of science. But in any case, this is the problem you would want to solve. So now we're minimizing over not maps, but couplings pi that have the property that essentially it's a bistochastic matrix. And I would like to minimize this sort of sum of distances in that case. And this is the bottom line is that this is sort of a challenging problem, to say the least, right? Very well studied, this sort of linear assignment problem. High complexity in the number of samples, typically at least n cubes. So instead, maybe about 10 years ago, Katuri proposed to regularize this with entropic regularization. This is coming out of observations around how to generate bistochastic matrices using Sinkhorn type algorithms. So basically you just add an entropy regularization term to your plan, right? Or your coupling when you're evaluating its cost. So talk about this offline. So this is essentially at the state of the art. This is what I think if you want to have a fast algorithm to compute optimal transport maps, you'll use entropic regularization. So what we're going to do is essentially compute the optimal transport maps with entropic regularization. That's this inner for loop in this algorithm for estimating the coefficients. And then once we have those, we're going to essentially compute the discrete analog of these integrals. Whereas we're going to compute an approximation to the matrix A by replacing the true maps with the entropic optimal transport maps given discrete samples. And we're going to replace the honest to goodness displacement integrals with Riemann sums, essentially. So we're doing the kind of obvious statistical thing here. The only wrinkle is we're adding an optimal entropic regularization in order to make this run faster. And the point is that it's consistent. So if we run this procedure, so what the main theorem here says that for each entry of the matrix A, this procedure is consistent, right? So if I use my entropic sample-driven estimation for Aij, that is converging an expectation to the true value. And I'll just say a little bit about these bounds, which is, okay, so the first term can essentially be ignored. It's not going to be the dominant one, it's the second term that dominates. So what you should see here is it's n to the minus alpha plus 1 over 4 times d prime plus alpha plus 1. Alpha is essentially, it's like a measure of smoothness of the transport maps in a precise sense. So it doesn't matter too much actually. But so the rate of convergence here is essentially like n to the minus 1 over 4 times the dimension of the data. So not great, right? It's a non-parametric rate, but it's not even n to the minus 1 over d. It's n to the minus 1 over 4d. So not sure if we can improve this. We're essentially leveraging some results of Niles Weed that are for this, and presumably better estimations of certain things you could plug and play with this. But yeah, for now, this is the strongest that we can get. And then the bottom line, though, is what we really care about is estimating the true barycentric coordinates given just samples. And one can use the above theorem and some random matrix theory to prove that actually the estimated coefficients is very close to the optimal one. So essentially, you can do this for real data. And I just want to say that it's pretty interesting what it can do for you. So I just want to show two of our applications. One is sort of a very sort of classical statistical problem, covariance estimation. So we're going to assume that what we see is, we're sampling from a Gaussian measure, mu naught. So, but we're going to assume mu naught's not an arbitrary Gaussian. We're going to assume it's in the barycentric span for some known Gaussians. So I know what those Gaussians are, but I don't know the coordinate. Okay, I don't know which of the barycenters of these possible Gaussians I'm sampling from. I just know it's one of them. Okay, and I want to know, can I do better in estimating the covariance matrix here than I could with methods that are, let's say, agnostic to the fact that this is a barycenter? And the answer is yes. And it's partially because the space of Gaussian barycenters has a bit of extra structure, meaning that in this precise case, if I have Gaussians and I take their barycentric combination, I know what the new covariance matrix has to be in sort of an implicit sense. So that's this corollary here. And I can use that property to be able to get better estimation of the covariance matrix than I could with the empirical covariance, right? So I can essentially solve the quadratic program given the, so essentially what I do here is I compute an empirical covariance matrix given samples, and then I plug that into my quadratic program to get an estimation for the barycentric coefficients. And then I return as my guess for the covariance matrix, the covariance matrix of the Gaussian I get from combining my reference measures with the learned coefficients. So the procedure is get a covariance matrix just empirically, the old-fashioned way, run our quadratic program and get some coefficients or approximate coefficients, and then use that to estimate the underlying Gaussian measure. And it works a lot better than the empirical estimation procedure where you would just take, the samples and do essentially, rank one sums to get the covariance matrix. And it's interesting because our algorithm actually works better than maximum likelihood estimation for the barycentric coordinates. So the gap between the green and the orange line is particularly interesting because it suggests that our quadratic program is within the universe of statistical procedures that make use of the fact that this is a barycenter, that this algorithm is a pretty good one. And I'll also comment, we don't have anything on here about this. Our method is extremely fast. Right, it's almost as fast as just computing the empirical covariance matrix. And it's because essentially it comes down to solving a small quadratic program. So very, very fast computationally, albeit suffers from non-parametric rates of statistical convergence. And the last thing I'll say is one interesting, we have sort of many applications in the paper, but one interesting application is natural language processing. And the reason this is so interesting is one can think about a document as a probability distribution of word space, where a document, I can take all the possible words, write out a histogram of how often that word appears in the document and get a probability distribution. So why not use the barycentric coding model here and see, okay, if I take documents from similar classes, right? If I look at a whole bunch of science documents or a whole bunch of sport documents or so on, will they look similar in the sense of having similar barycentric coordinates when I represent them with respect to a fixed set of reference measures? So we ran an experiment to do this. Right? I'll note that all of this is not on the original word space. We use standard NLP word embeddings to reduce the dimensionality to about 300. So we made some comparisons. And what we're seeing here is, okay, so I have 20 different news topics from a standard data set. And what I'm going to give you is for each of the topics, a small number of reference measures, right? So 2 measures from each class, 3, 4, 5, and so on. And then new measures are going to come in, right? New documents. and I'm going to compute the barycentric coordinates with our method. And I'm going to show you the results of classifying based on which coordinates have the associated smallest loss in green, and which coordinate, what was the class of the maximal coordinate in red. And what we're seeing is that those are quite a bit better than classifying based on one nearest neighbor distance to my reference documents in Wasserstein space, and also quite a bit better than for each observation that I want to classify, computing its average Wasserstein distances to these different classes and making that decision. And so the gap between the green and the red here is really interesting, because it says that my interpretation is combining using this barycentric idea gives you information, right? We're not just computing, we're actually making decisions based on stuff that wasn't observed, right? We're actually looking at, oh, okay, if I compute something in this barycentric span that was not close to one of the original documents, does that give me better representational power? Am I doing good representation learning here? And I think the answer is absolutely yes. So I'll just say that there's some interesting open problems related to, what's the capacity of this thing, right? Like, can I represent arbitrary measures? If I take enough measures in my reference set, all of this, we just pick as our reference measures random samples from the data set. Can we do better than that? Can we learn some things? So the first part of the talk, I just want to acknowledge collaborators, is with Anna Little at University of Utah, Mara Majoni at Johns Hopkins, Dan McKenzie at UCLA. And the second part of the talk is with some collaborators at Tufts, Shuchin Aaron and Rongji Zhang in electrical engineering, and Abby Tassisa in mathematics, and Matt Borensky in electrical engineering. So these are the papers. Thank you for your support, and some code is on my website. So thanks for your attention, everyone.
Thank you, James, for a very interesting talk. So any questions from the audience?
I have a quick question. I
Hi,
have a couple questions, but I'll make sure to take turns in case other people have questions too. I found the last example really interesting in terms of the application of natural language processing. How sensitive did you find that your results were to the choice of the reference measures you picked for the barycentric projection? And were there any kind of guiding principles for the selection of those reference measures?
Good question. We didn't find it to be too sensitive, right? Especially, obviously the sensitivity was lowest when you had 2 reference measures per class, and that variance was sort of washing out as it got bigger. But we didn't find it to be too sensitive. And in fact, these experiments are averaged over, so the way we conducted this is we would say, okay, fix your training data if you like, right? Fix the reference measures for each class, and then take many testing samples and compute accuracies, and then redo the training set, right? So this is sort of like a second layer of kind of validation on this, in which we averaged over that. I think that one of the things we're trying to understand is, how do we pick these reference measures, right? I think so far we've been, not really so concerned about getting the smallest possible set of reference measures that get it done. There's an interesting kind of question of can you learn them, right? That we kind of know, we have a good condition of what it would mean to represent well in this setting. So one could try to do dictionary learning, right, in the space of measures here, where your loss would essentially be this kind of barycentric error, right? You would say, well, set of dictionary atoms is going to be good if, when I combine in this way, I can, on average, represent everything really, really well. That's definitely a hard computational problem. I would say that's where our bottleneck is there. There is a pretty great paper on this. I think it's just called Wasserstein Dictionary Learning, but it's very, the computational aspects are significant here, at least so far for us. So we don't have a whole lot of guiding principles besides that, but would be a good thing to do.
Oh, so any other questions? Yeah, we'll
Yes,
talk.
I have more. Is there an interpretation of the barycenter problem in terms of the linearization of the Wasserstein metric around the measure mu naught that you're trying to project onto the barycenters?
Oh, I don't know too much about that. I just read something. You're referring to like, you're using like the H-1 norm. Right?
No, that is also a linear. You're right. The word linearization is used too much. I just meant I'll send you a reference. I think there may be a connection between what you're doing and a different notion of linearization of Foster-Stein metric at the mu naught. And it's probably just like I don't think it's a deep connection, but I do think there's like a superficial connection between the two. So that'd be great. Kind of a fun, I think it could be a fun perspective on it, what you're doing. Okay, I'll pause for a moment, and then I have one more question.
So any questions from the other audience? Yeah, let's thank James. Yeah.
Okay, hold on, one more.
Okay.
More. Okay, for the first half of your talk.
Yeah.
So my background is a PDE background, so my brain is always like at the continuum. And so sort of how I love the interpretation of what you're doing is kind of manipulating the underlying distance on the space. And so would there be so how you presented the problem was keeping the Laplacian the same, keeping the notion of graph Laplacian the same, but modifying the distance, modifying the notion of distance on your underlying space.
Yes.
I guess, and indeed, it does seem that by incorporating density information in certain clustering applications, incorporating more density can help you identify better clusters. I guess my question is it seems like from the continuum perspective, this could be accomplished in a similar way by modifying your notion of the Laplacian by like conjugating on the appropriate side by the degree matrix to get the same continuum equation of the continuum. And I was just wondering if you had thought about sort of the pros and cons of those. I feel like you could incorporate density information in the same way, but I don't really know much about it aside from the fact that they seem like they coincide at the continuum level. So I don't know how their behavior would be different at the discrete level.
Yes. Yeah. I mean, I think that great question. What I think is definitely true is that if you were to consider something like LP to the P, right, where you don't have this sort of like rescaling by taking this like 1 over P exponent, then this winds up being quite similar to basically conjugating by different powers of the degree matrix, right? And where the power would somehow correspond to P. Something that is a little bit different, I think, is when you have this 1 over P on the outside, this gives it kind of a non-local quality when P is large, right? In the sense that it will make things look very, very close that are in Euclidean distances very, very far away when you define equation 1 this way and P is large, because it essentially compresses along regions of constant density, right? So in that case, if you're using this definition, I believe there will certainly be a difference between doing just conjugating by the degree matrix, which is very, very local. I
missed the 1 over P on the outside.
But this is our challenge actually, is we have a much easier time handling LP to the P because you can do essentially what you said, right? You can try to connect this to different ways of just normalizing by the degree matrix, right? With maybe sort of insanely large powers on it or so on. But it's been easier for us to do the analysis for. And you're right that there is a very close connection between those things. I wouldn't say we have like kind of the one-to-one connection down, right? But you're right that I think there's spiritually at least a very, very strong connection. With the 1 over P, it's a lot, I think the story becomes more of a non-local one. So in that sense, it's more interesting, but I think has admitted less analysis to us.
Thank you.
Any other questions from the audience? If not, let's thank James again.